In this lesson, we're going to apply what we learned when we were solving linear inequalities and start to solve polynomial inequalities. So where instead of having just a linear function, we're going to work with functions of a higher degree. So let's start off with graphically taking a look at two polynomial functions. One is called f of x and one is called g of x. So f of x is defined by this polynomial and g of x is defined by this polynomial here. And we're to determine when f of x is less than g of x. So this might be easier if we can maybe highlight which function here is f of x and which is g of x. So let's add a highlight of, we'll say, red under the f of x function, and we'll highlight g of x as blue. So now that we have the functions highlighted, it's easier to see when one is greater than the other. So what does f of x less than g of x mean? Well, it means when are the y values of f of x less than the y values of g of x along its domain. So specifically, what are the x values so that the y values of f of x are less than g of x? So now let's determine the solutions graphically. To figure out what the solutions are, let's first figure out when f of x is equal to g of x. Taking a look at this, it looks like we've got three intersection points. We've got one intersection point at x is equal to -1. We've got another intersection point at what looks like x is equal to +2. And another one at when x is equal to +3. So those are going to act as our critical points. We know something changes at each of these points of intersection. So we're going to take a look at the interval when x is less than -1, when x is between -1 and 2, when x is between 2 and 3, and when x is greater than 3. So let's take a look at each interval individually. Let's take a look at this interval here, when x is less than 1. So according to our graph, we can't tell if there's a point of intersection after this. So let's just assume this is our last point of intersection. So in this interval here, our g of x is greater than f of x. So in this, another way to say that is f of x is less than g of x. And that's what we're looking for. We're looking for the interval in which f of x is less than g of x. Let's take a look at this next interval here. We can see now the y values of f of x are greater than g of x. The reason why I continue to write f of x first is because that's how the question was phrased. So it's going to be easier for us to figure out when is this true if we just write f of x first. Let's take a look at this next interval. We can see that the polynomial, the y values are very, very close to each other, but g of x is slightly greater than f of x. So if we write f of x first, we would say that f of x is less than g of x here. And then finally, let's take a look at our last interval. We can see f of x, which is our red function, is greater than the y values of g of x, so f of x is greater than g of x. So now that we've worked all that out, let's just figure out what intervals did we actually find, or the values of f of x were less than g of x. Well, we have one interval right over here, when x is less than -1, and we've got another interval right over here, when x is between 2 and 3. So here's our final solution. F of x is less than g of x when x is less than -1 and x is between 2 and 3. If we want to write it in interval notation, we could do the same, and it would look like this. Now let's take a look at the exact same example with f of x and g of x, but let's solve it algebraically and see if we come up with the same solution we came up with graphically. So we're to determine when f of x is less than g of x. So let's set up our inequality. So now we're ready to solve this. Think about what we would do to solve this if this was an equal sign. If this is an equal sign, we bring all of these terms onto the other side, or all of the terms onto one side, so one side's equal to 0, and factor it. We're going to do the exact same thing with an inequality. Let's bring all of the terms from this side of the equation onto the other side, so that our right side is equal to, or our right side has a 0 there, and then we can factor. So we're going to have 2x cubed minus x cubed, and then minus x squared, subtract 3x squared, plus 3x, subtract 2x, plus 10, subtract 4, and that's all going to be less than 0. So on the left side, we have x to the power of 3 minus 4x squared, plus x plus 6 is less than 0. So if this was an equal sign, what would we do next? Well, we would factor this so that we could solve for the values of x, so it would make the function equal to 0. So let's factor it and see what happens. So we can try grouping these four terms together, but there isn't a way to factor it by grouping, or at least it's not an easy way to factor it by grouping, so we have to use the factor theorem. If you remember the factor theorem, when our leading coefficient is 1, our possible factors are all factors of our final constant term 6. So think about what are all of the factors of 6. Well, we have plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. So recall, the remainder theorem says that if we were to plug in the 0 of one of the factors into this function right here, it should give us 0. So let's try plugging in plus and minus 1, plus and minus 2, plus or minus 3, plus or minus 6 into this equation here and see what's going to give us 0. So I found f at 3 equals 0. You might have found that f at 2 is equal to 0, f at negative 1 is equal to 0. All of those are correct answers. So there's actually 3 solutions. Let's just go with this one. So when we plug in 3 into the function, we get a remainder of 0. Therefore, the factor must be x minus 3. And now that we have one factor of this polynomial, all we have to do is divide x minus 3 into this polynomial function to come up with the other factors. Because we're dealing with a linear factor and the coefficient is 1, we can use the simple version of synthetic division to do this. So if you remember how to set it up, we're going to do our little L. Up here is our 0 of our linear factor, which is going to be 3. Then across we're going to put all of our coefficients of each of the coefficients of the polynomial function that we're dividing into. So we have 1, negative 4, 1, and 6. We're going to drop down the 1, multiply 3 times 1, which is 3. Add these together. Negative 4 plus 3 is negative 1. We're going to multiply 3 times negative 1. We get negative 3. Add these together. We'll get negative 2. And then we have 3 times negative 2 is negative 6. Add these together and we get 0, which is what we expected because that's our remainder. So here is our remainder. Here is our constant. Here is our x term. Here is our x squared term. So when we divide these two, we get a solution of x squared minus x minus 2. And can we factor this again? Well, are there two numbers that multiply to negative 2 and add to negative 1? And there are. It's negative 2 and positive 1. So we can factor this to x minus 2, x plus 1. So let's summarize what we found. Here is the equation we were working with. So let's copy that down first. Now we factored this guy into 3 factors. First, realize this was a factor. When we divided this guy into this polynomial, we got x squared minus x minus 2. And then we were able to factor that even more into x minus 2 and x plus 1. So now we have a bunch of x values that can come out of this. We have x is equal to 3, x is equal to 2, x is equal to negative 1. Those are not the values that are going to make it less than 0. Those are the values that are going to make this equal to 0. Those are our points of intersection. So x equals 3, x equals 2, x equals negative 1 are our points of intersection, as if we were to solve this with an equal sign. So now that we've solved for our points of intersection, which are exactly the points of intersection we found when we looked at this graphically, now we're going to have 4 different intervals that we need to check. So here are our critical points. So if we were to map this out on a number line, here are our critical points that are determined by our points of intersection. We want to check out this interval. We want to check out when x is less than negative 1. We want to check out when negative 1 is less than x is less than 2, so when x is between negative 1 and 2. We want to check when x is between 2 and 3. And we want to check when x is greater than 3. So the idea is we need to satisfy this simplified equation. that is the same equation that we were dealing with at the beginning of the lesson, right up here. This is our original inequality that we need to satisfy, and this is just a simplified version of it. So whatever satisfies this inequality is also going to satisfy this one because they're equivalent. So now that we have our intervals that we're going to check, all we have to do is choose points in each interval and plug it into this guy right over here and check if the entire solution will be less than 0. If it is less than 0, then it satisfies this inequality. So one way to do that is just to pick points in each of these intervals and literally plug it into our inequality and check if those points satisfy this. So if I were to plug in, let's say, -2 from this interval right here, something that's less than -1 is -2. If I were to plug in -2 here, I just have to check, does it actually give me a number that's less than 0? If it does, then this interval is one of our solutions. Another way to do it is in a similar way, but just setting up a table to help us organize ourselves. So at the top of the table, you can put our intervals. On the side of the table, we've broken this up into factors, and we just need to check actually the sign of the factors to check if it's less than or greater than 0. So here's what I mean. On the side here, one way we can organize it, just put our factors. So x minus 3 is a factor, we have x minus 2 as a factor, and then x minus 1. Sorry, x plus 1. And then we need to see the total. So let's choose a number that's in this interval to get started. So a number that's less than -1 is -2. That's nice and easy to work with. So all we're going to do is we're going to plug in -2 into each of these factors, and we don't need to know the value of the factor. We just need to know if it's positive or negative, because we're just checking if our final solution is negative, if it's less than 0. So if we multiply the signs, positive or negative, together, we can predict if this guy's going to be positive or negative. Here's what I mean. If I were to plug in -2 into this factor here, we would get a negative number, because -2 minus 3 is -5. The number doesn't matter, the sign is what we're looking for. Take a look at the next one. If I were to take -2 and subtract it by 2, I would get again a negative number. And then if I took -2 plus 1, again a negative number. And if we multiplied all of these together, like how they appear in the polynomial function here, we multiplied negative times a negative times a negative, it would make again a negative, which means that this function would be less than 0, which is what we're looking for. We're looking for the intervals where this function would be less than 0. Let's take a look at the next interval. So let's pick a number between -1 and 2. An easy number would be 0. So if I plug in 0 minus 3, I'd get a negative, a 0 minus 2, again negative, and a 0 plus 1, I'd get a positive. If I were to multiply them all together, like here, a negative times a negative is a positive times another positive, we get a positive number. So in this case, that function is greater than 0, which is not what we're looking for. So if you'd prefer to actually find the value when you plug in 0 rather than just the sign, you could do that, but just finding out whether the answer will be positive or negative is a really fast way to check this. Let's figure out, let's do these final two. So we're going to pick an x value that's between 2 and 3, so we can pick 2.5 and plug them in. So we've got 2.5 minus 3, that's going to give us a negative number. We have 2.5 minus 2, positive. 2.5 plus 1, another positive, and the result would be negative, because a negative times a positive would be negative. So which is what we're looking for. This function would be less than 0. And finally, we know what's going to happen here. But let's just check. Let's pick a number that's greater than 3, like 4, for example. And let's plug in 4 into each of our factors. Well, 4 minus 3 is a positive number. 4 minus 2 is also a positive number. 4 plus 1 is positive, so the result would be positive, and this function would be greater than 0. So we are looking for when the function is less than 0. So here are our two solutions, our interval solutions. So in conclusion, we have two solution sets for this inequality here, when x is less than -1 and x is between 2 and 3, which is exactly what we found graphically. So to summarize everything together, where did we get started? We started with this inequality and we subbed our polynomials into it, and we just started to solve it, and we solved it by exactly the same way we would do if there was an equal sign here, bringing everything onto one side. So then we factored it, and this was our solution. So we have different x solutions, but they're not solutions to this inequality. They're solutions to make it equal to 0. So there are points of intersection. So we pulled out our points of intersection, which we know are our critical points, which told us what intervals we wanted to look at. So we wrote them on to our number line here. We knew we need to look for when x is less than -1, between these two, and greater than that. So we could just plug in numbers into this inequality and check if it's less than 0, actually find the value, or we can set ourselves up with a nice chart just to check the sign of each of the factor. The chart might take like a 10 seconds to set up, but sometimes it'll just make it easier, and there'll be less chance of a calculation error. So once we check the sign of the value of this function, we could figure out when it was going to be less than 0, and here are our two interval solutions. Now that we understand the basics, let's try this next inequality. So here we're already given a simplified inequality, so we're not taking a look at two functions either side. It's already been simplified, and we're checking when this polynomial function is greater than or equal to 0. So because it's already simplified, we don't need to do that step, but we do need to factor this. So this one, we can use the factor theorem again, but this one's a little different because our leading coefficient isn't 1. So we need to check what all the factors of this guy are, all the factors of this guy, and then divide them one on top of the other, which is going to give us a bunch of different combinations. So what I'm going to do is I'm going to give this to you factored. If you need practice with how to factor this, just be sure to take a look at our previous lessons on the factor theorem. Now that we have this factored, we can determine what the solutions of this would be if it were equal to 0, and those are going to be our critical points, the points we're going to look that are going to determine our intervals. So what are actually the solutions if it were equal to 0? Well, we would have x is equal to 1/2, x is equal to -3/2, and x is equal to -4/3. So these will make up our critical points. If we want to just organize ourselves on a number line, we have -3/2 over here, and then we have -4/3, and then we have 1/2. So we're going to take a look at this interval here. We're going to take a look at between these two values, and anything that's greater than 1/2. So let's set up our chart. So now that we've got our intervals at the top, our factors here, we can quickly tell whether our result is going to be positive or negative. So let's pick a number that's less than -3/2. So why don't we pick -2, for example. If I were to plug in a -2 here, our result would be negative. If I were to plug in a -2 in the next example, it would still be negative, a negative here, and our result would be negative. Again, all I'm doing is I'm plugging that -2 into each of these factors and quickly determining if the result would be positive or negative. So this result would give us a solution that's less than 0. In this case, we are looking for a solution that is greater than 0. So this interval is not going to be part of our solution set. Let's take a look at this guy. We know that this is -1.5. We know that this is approximately -1.333. So they're quite close, but let's just pick a number that's in between, like -1.4. If we would plug in a -1.4 here, our result would be negative. If we plugged in a -1 here, our result would be positive. And a -1.4 in here, our result would be negative. And if we multiply all of these together like they're laid out here, we would get a positive result. So our solution would be greater than 0, which is what we're looking for. I just realized we missed one of our intervals up here. I missed one of our intervals. We forgot about this guy right here, so I'm just going to add it in. So let's erase this one. I'm going to add in the interval between -4/3 and 1/2. So -4/3 is less than x is less than 1/2. And then we'll put back our final interval, which is x is greater than 1/2. All right, let's quickly finish up these guys. So let's pick 0. 0 is a part of this interval here, and quickly plug in 0. Plugging in 0 here will result in a negative solution. The next one will be positive, and the next one after that will be positive as well. So if we multiply all these together, we would get a negative result, which would make our function less than 0. And last, let's pick a number that's greater than 1/2. A number that's greater than 1/2 that's easy to work with is just 1. Let's just plug in 1 into this function. So we'll plug it into each of these factors. 2 times 1 minus 1 gives us a positive result. Our next factor would also give us a positive result, positive, and we have our function would be greater than 0. So remember, we're looking for whenever the function is going to be greater than or equal to 0. So that's going to work out in this case over here, greater than 0, so this guy right over here, and this guy here. So we're going to have two solution sets, and these are them. But there's something missing from our final solution, and that's because we're to check for solutions where this function would be greater than 0 but also equal to 0. So these critical points are points where this function would be equal to 0. So we're going to include negative 3 over 2 and negative 4 over 3 because that will set the function equal to 0, as well as include 1/2. So we're just going to put little equal to signs here. And we're done. Let's try this last example together. So I'm going to help you with factoring this guy. Remember, if you have trouble with factoring this, go take a look at our previous videos on using the factor theorem when our a value or leading coefficient is not 1. One thing I am going to do is, before we factor this, I want a leading coefficient of that's positive. So I'm just going to divide both sides by -1. And we remember that when we divide an inequality by a negative number or multiply an inequality by a negative number, we need to change the sign here. So this is going to change from a greater than sign to a less than sign. So here's what our polynomial inequality looks like now. Note that we've got that sign change and everything's been divided by -1. So now factoring this is super fun because it's a degree 4 and we're going to have to use the factor theorem not once, but twice. And on top of that, we have these leading coefficients and constant terms that are very large that have many factors. So be lots of possibilities. So what I'm going to do for you is I'm going to factor this for you. Remember, if you need practice, go to the previous video. So also when you're working on this and you want to quickly factor something, don't forget that you can use the website Wolfram Alpha and just type this guy in and it will factor it for you. So now what we can do is we can pull the solutions to this equation if it equals 0, or our critical points. And our critical points are going to be 2, negative 5 over 2, positive 1 over 3, and negative 2 over 3. So if we were to transfer these to a number line just to organize ourselves, our highest value is 2, and then we have a third, and we've got negative 2 over 3, and negative 5 over 2. So here are going to be our intervals that we're going to check. We're going to check less than negative 5 over 2, in between these values, and this over greater than 2. So now we've got 5 intervals to check. So make a chart, solve this on your own, and when you think you've got it, come back to the video to check your solution. So now that you've come back to the video, you've either figured out your solution sets using this chart, or maybe you've come up with your own way where you're plugging in different values. As long as you come up with these results, which is that in this set of x values where x is less than negative 5 over 2, we will get a positive answer, so our function will be greater than 0. We're looking for it when it's less than 0. In this interval, our solution will be less than 0, so this is one of our solution sets. In this interval, our result will be greater than 0. In this interval, our solution will be less than 0. Again, that's one of our solution sets. And in this final interview for all x values greater than 2, we would get a positive result. So we have 2 intervals that satisfy our inequality that this function has to be less than 0, and here they are. So here's our final solution.